Infrared spectroscopy. So this is another way of determining what kind of substance you may have. So you've got an unknown substance and you've got to determine what it is. So mass spectrometry can tell you what the molecular formula is. So roughly how many carbons, hydrogens and oxygens you might have in there, and it's MR, it's mass. So from its mass you might be able to determine what kind of molecular formula you have and what kind of MR you have. That's what mass spectrometry does. Infrared spectroscopy goes a little bit further. Infrared spectroscopy uses infrared light, and what you do is you shine the infrared light through the substance. You don't know what the substance is, that's what you're trying to do. You're trying to determine what it is. Some of the light energy is absorbed by the substance. It's used to bend and stretch the bonds that are in that substance. So say for example, if the substance was CH3, CH2, CH2OH, if we look at the different kinds of bonds in there, I've got carbon to hydrogen bonds, I've got carbon to carbon bonds, I've got carbon to oxygen bonds, and oxygen to hydrogen bonds in there. I've got different kinds of bonds in this chemical, in this substance. So depending on what the substance is, the light energy, the infrared light, is used to bend or stretch some of these bonds. And depending on what kind of bonds you've got in there, how much bending or stretching they do, depends on the light that's absorbed. So the light that's absorbed, if no light were absorbed, this line would be horizontal at 100% transmittance. Transmittance means how much comes through. But it has dips. The dips are called troughs. So here, some of the light, right down to hardly any of this light, is being transmitted. That means that something in this chemical, some bonds in this chemical, are being bent or stretched. Here again, we've got a massive dip, a massive trough. So that means that this light here is being absorbed by bonds in this chemical that are being bent or stretched. And then there's some more here as well, and then it seems to go all a little bit fuzzy over here. Now, these are at different wavelengths, wave number or wavelength. So light has different wavelengths or wave numbers. If you notice the scale on this graph that comes out of the infrared spectrometer, the infrared spectroscopy machine, goes back to front, so it goes large down to small. That's just a sort of quirk of the machine. So it reads from large down to small, and depending on the wavelength of the light, we can look up what kind of bonds are in this chemical, because certain bonds absorb light of different wave numbers or wavelengths. So I know that this wavelength or wave number here, around about 3,300, 3,400, remember you're reading this way, right to left, so 3,000, 3,100, 3,200, 3,300, 3,400, around about 3,300 to 3,400 wavelength, wave number of light is being absorbed. So if I look up in a data table what kind of bonds absorb that wavelength, wave number of light, I will know that they are in this substance that I'm trying to identify. And I can find out when I look up in a data table that OH bonds stretch or bend at this wave number of light, at this wavelength of light. So I know that in this chemical I've got an OH. Here, at around about 3,000 wavelength, that's a carbon to hydrogen bond stretching or bending when I look it up. So now I know I've got an OH, it's an alcohol, and I also know that I've got a CH, so it's got some carbon to hydrogens. And I've also got some carbon to hydrogens here as well. And then I've got this whole region over on the right. So the wave number or wavelength of light absorbs tells you the bonds that are present. They're present because those bonds bend or stretch and absorb some of the light. That's why we get these troughs, and you can identify the substance that you have. It's used in combination with a mass spectrometer, and so by doing infrared spectroscopy and mass spectrometry, you can find out the MR and therefore what kind of groups are present. So the MR through the mass spectrometry and the groups that are present through infrared spectroscopy, and you can then find out, probably determine what kind of chemical that you've got. Sometimes, however, it's still hard to tell exactly what substance is present. Say, for example, I know now that there's no H there, but I don't know exactly where it is. Is it on carbon number 1, or is it on carbon number 2? I've got its MR from my mass spectrometry. I know that there are 3 carbons, I know how many hydrogens in there, and an oxygen and a hydrogen, but I don't know where this OH is. It could be a positional isomer, and it could be on carbon number 2. That would have the same MR. It would also have an OH, but the OH would be on carbon number 2. So how do I know where it is? So I've determined that it's propanol, but I don't know whether it's propan-1-ol or propan-2-ol. Well, what you can do is you can use this fuzzy region here. This region that seems to be not very good because it's all got lots of troughs very close together. It's a little bit fuzzy, a little bit hard to read. This is called the fingerprint region. So this region here, anything less than 1500 wave number is called the fingerprint region. So anything from 1500 across to the right is the fingerprint region. This is very useful because what you can do is, when I think I know what it is, but I'm not completely sure, I don't know whether it's propan-1-ol or propan-2-ol, I run a sample of propan-1-ol through the machine, and I run a sample of propan-2-ol through the machine, through the infrared spectroscopy machine. And this fingerprint region, just like a fingerprint on your finger, is different for you compared to somebody else. It's unique to you. And so this fingerprint region here would be different for propan-1-ol and different for propan-2-ol. The rest of it is the same. They've both got an OH group, they've both got carbon to hydrogen bonds, and they've both got identical MRs. So when you run it through a mass spectrometry machine, a mass spectrometer, it would have identical MRs. But this part, the fingerprint region, is different depending on what chemical you've got. It's unique to a particular chemical. So when I run propan-1-ol through the infrared spectroscopy machine, and then propan-2-ol through the infrared spectroscopy machine, this fingerprint region is different. And so I can compare my unknown, so I'm not sure what it is, I compare my unknown to the graph that comes through when I run propan-1-ol through, and I compare my unknown to the graph that comes through when propan-2-ol runs through the machine. I find out that these are different, and I can find a match. So I compare my unknown graph against the graphs from known substances to identify them. Incidentally, the sun releases infrared light. Greenhouse gases like carbon dioxide, methane and water are good at absorbing this light, and this is what causes global warming. The carbon to oxygen bonds and the O2H bonds in water absorb infrared radiation, and that does not allow it to escape from the Earth's atmosphere. So nothing really to do with infrared spectroscopy, but linked to this idea that bonds absorb light to bend or stretch bonds, and that's what some of these gases are doing when they absorb heat energy, infrared light energy from the sun. So infrared light energy gets absorbed, these gases warm up, and by absorbing the infrared light and warming up, that causes the Earth's atmosphere to warm up, and that is, of course, the greenhouse